Welcome all. So today we will be discussing the problem number 7 from TIFR 2020's paper. So this problem, as you can see, it's been given in the form of integration, but there are several ways to do it. The method that I will be using in this video, it will be, it is basically a direct descent from the inequalities. So we will be using this property very heavily. So if I have f1 less than or equals to f2, then integral of f1 is less than or equals to integral of f2. Okay, and also if the same thing, like if let's just for the sake of notations, if g1 less than or equals to g2, then limit some x tends to infinity, the inequalities remains same. All right, so the inequalities do not differ. So as you can see, there are two things to take note here. One is am itself, because that's where our final answer where our final answer will come from, and another is the choice of the function log of 2 plus x root over of 1 plus x. All right, so what we will do is, first we will try to establish a chain of inequalities. So first we will try to establish the chain of inequalities, and then we will move towards the solution. So see the function f of x, it is given to us as log of 2 plus x by root over of 1 plus x, and it is also mentioned that x is greater than 0. So if you look at this, then x is greater than or equals to 0. All right. Now the fact is that since x is given to be greater than or equals to 0, what we have is something like this, that log of 1 plus x, it will be strictly less than or equals to log of 2 plus x. Because see, it is an increasing function, right? So in the first quadrant, it becomes an increasing function. So this actually comes from there, and since 1 plus x is always less than 2 plus x in the first quadrant, we will just use the increasingness of log, and we will have this inequality. So now if I take this 1 plus x and root over of 1 plus x, everything remains as it is. So let's call this as 1. Now again, we all know that since x is greater than or equals to 0, 1 plus x is greater than or equals to root over of 1 plus x, right? So from here, what we will see, from here we will see that 1 log of 1 plus x by root over of 1 plus x, this is strictly greater than or equals to log of 1 plus x by 1 plus x, by just using the whatever happens in an inequality whenever we are taking the inverse. Hence, if I now take these two inequalities 1 and 2, if I take these two inequalities 1 and 2, and then do it like this, then just put it like, then let's just put it like this, log of 1 plus x by 1 plus x is less than or equals to log of 1 plus x by root over of 1 plus x less than or equals to log of 2 plus x by root over of 1 plus x. So as you can see, if I put the integrals now, 0 to m 0 to m, 0 to m, all these integrals. And what is the last thing to do? To add limits. M tends to infinity, limit m tends to infinity, limit m tends to infinity. So what we are trying to find? So the first half suppose the first half of this inequality, after taking the integration and then the limit, if it goes to infinity, then by the law of the integrals inequality that we have just seen, this term, which is our required term, I mean, which is one of the required, it is basically the numerator, that will also tend to infinity because of the inequalities, right? Because if my left if my leftmost side tends to infinity, then a function whose functional values are greater than or equals to that, it will also go to infinity, right? So, and of course we know that log 1 plus x by 1 plus x, this will go to infinity if you take 0 to m, limit m tends to infinity. This is the standard log x by x, uh, log x by x integral. Okay, so you can actually do it by taking like log x. So here how will you do it? By the method of substitution. I think that's pretty straightforward. You will take log of 1 plus x equals to z, then 1 by 1 plus x becomes your, so dx becomes your dz. So then this integral is nothing but 0 to m z dz. So from there you can kind of understand that if m tends to infinity, this integral, it will tend to infinity. So now let us come back to em. So what has been given? Em, it is limit m tends to infinity, integral over 0 to m f of t dt by m. Now if I want to use the L'Hospital rule or L'Hospital rule, so what is the thing that we want? We want an infinity by infinity or 0 by 0 form. The numerator, it tends to infinity by this inequality that we have just shown, because by this inequality, using this inequality, we can show that the numerator, we can show that the numerator goes to infinity. So the moment numerator goes to infinity, the denominator also goes to infinity as limit m tends to infinity. All right, so that means I have the infinity by infinity form, hence I can actually use the L'Hospital rule. So by using L'Hospital's rule, what do I have? So this is exactly this is the theorem that we have used in one of the earlier problems as well. It's this, that if you have phi 1, phi 2, f, then if you take ddt, so it will be f of phi 2 prime minus f of phi 1 prime. Okay, so that is the standard rule. So here we will be taking, instead of ddt, we will be taking ddm. All right, so if I take ddm, what will happen? So if I take ddm, then we will have this, that it will become f of m, then ddm, it is 1, then minus 0, the denominator becomes 1. All right, so the denominator becomes 1. So if you take this, then what you have, so this is limit m tends to infinity, f of m by 1. So now our goal is reduced to proving this. So what we wanted to show at the beginning, so at the beginning we wanted to show what is limit m tends to infinity em was. Now it suffices to show show that what is limit m tends to infinity f of m is. All right, so let's just get on to it. So we will use just L'Hopital's rule once again. So f of m is log of 2 plus m by root over of 1 plus m. So limit m tends to infinity, this will go to 0. Why? You can actually use twice the L'Hopital. So here 1, here 1. So if we use L'Hopital twice, the everything or in everything that contains m will be in the denominator. Okay, because if you use it once, then what happens at the first step, you get something like this. All right, so still this is an infinity by infinity form. You will do it again. So what will happen then? So you will have something like this. All right, so this is just L'Hopital's using twice. So taking differentials here, taking differential here once, then we get here, then taking differentials of this and this the denominator we get here. Now this limit m tends to infinity tends to 0. Thus our what was sufficient to show becomes 0. It becomes 0. All right, so what did we use here? Now these type of things are very much important if you are looking for competitive exam questions, because see there you won't have much time to compute the integral and do stuff on your own. All right, so that is why these type of inequalities actually makes your life easy, because see the only tricky part was to get to this inequality. After that it's just basic plus to level L'Hopital rule usage. Okay, so hence the solution to this question is, the solution is question number 4. Sorry, the option D, that's the solution. And that concludes our today's discussion. We will meet with another TIFR problem in upcoming days. Thank you for joining me, and Cheenta's college math admissions are open. It's for people who are preparing for master's level competitive exams, and the current course that is going on are point set topology and real analysis. Thank you for joining.